Hello, Mrs. Teasley here. Today we're going to be talking about radicals and rational exponents. Here I have a chart. This is a chart of perfect numbers. I know it looks like a whole bunch of just numbers, but what you're really going to focus on is this first column. All right, this first column is going to be where your answers are located. So what this means is if you look here, you have the x squared, x cubed, x to the fourth, x to the fifth. So let's just take a number. Let's look at 36. This means that the square root, all right, so the opposite or the inverse of squaring something is going to be a square root. So if I do the square root of 36, that's going to equal 6. The cube root in this column of 216 equals 6. The fourth root of 1,296 is 6. All right, so hopefully you have the idea. So let me erase my little circles. So this first column are your square root numbers. So this is going to be my square root numbers. So square root, we don't write this index. All right, the cube root, so this little number we write is called the index. You have your fourth root of x, and then you have your fifth root of x. X being any of the numbers, any number. So let's look at another number. So if I wanted to know what the fifth root of 243. So the fifth root of 243, if I come over here, that's on this row. So the answer is 3. If I wanted to know what the cube root of 512 is, so cube root 512, then that answer equals 8 because it's on this row. So your answers is always in that first column. One more, the square root of 225 is 15. So this chart is really going to come in handy as we work through this lesson on radicals. So these are your perfect numbers. All right, so radicals. So what in the world is a radical? So radicals, most people know square roots. All right, a square root is a type of radical. But then you have the higher roots, cube roots, fourth roots, fifth roots. Those are also all radicals. So you have this n, and you have the number underneath. The n is the index, as I mentioned earlier. And then the number underneath the radical symbol is the radicand. Make it a little bit better. All right. All right, I'm sorry, y'all. That's just ugly. So A is the radicand. All right, so it just talks about, so the nth root of a equals b. That means b to that power equals a, and that's kind of pretty much how that chart works. So for example, if I have that the square root of 4 equals 2, this also means that 2 to the second power equals 4. All right, so let's look at some examples. All right, so starting off with example 1, we want to evaluate. Now, the square roots, you might know these. These are, most people know, like the perfect squares. So the square root of 81, if I just want to use my chart, I'll look at my square root column, see if I see the number 81. Bam, there it is. The square root of 81 is 9. So this equals 9. Same thing, the square root of 169. If you go to the chart, if you don't know it, the square root of 169 is 13. When it comes down to fractions, the way that you take the square root of a fraction is you want to separate this and do the square root of the top number or numerator over the square root of the bottom number. So the square root of 1 is 1, and the square root of 25 is 5. So that's how we deal with fractions. So whenever you have a positive index, so in this case, let's talk about this index, n, which is our index equals 2. So if you have an even index, and negative radicand, you're going to have a non-real answer. So non-real answer. So in my math lab, if you were given a problem, what's the square root of negative 36? The answer would be that it's a non-real answer. And that's because the index is an even number, and the radicand, the number underneath the radical symbol, is negative. So for example, if I wanted to find, let's do the fourth root. If I wanted to find the fourth root of negative 16, right? And if you look underneath the fourth root column, you see the 16. Let me erase this. So you see the 16, all right? In this case, it's negative. So 16 is a perfect root when it comes down to fourth root, but because you have a negative 16 and that index is a 4, the answer would be non-real. So this is also non-real. So this is non-real. Now, let's talk about something like the cube root. So here I have the cube root of 64. So let's look at the cube root of 64. So if I go to my table, I'm going to look in the x to the third power column, see if I see the number 64. So this can kind of, so here if I come here, here's my 64. Well, the cube root of 64, the answer is in this column is 4. All right, so the cube root of 64 equals 4. All right, what about if we look at something like the cube root of negative 125? All right. If you have an odd index and a negative radicand, your final answer is negative. So basically, when it comes down to the cube root of negative 125, it's going to be negative something. Well, what is the cube root of 125? So it's going to be negative, all right, the cube root of whatever 125 is. So the cube root of 125, if I go to my chart, I look and I see I'm looking for 125 in the x to the third power column. Here it is, 125. The cube root of 125 is 5. So in this case, since my radicand was a negative 125, this becomes negative 5. All right. So what I want you to do is pause the video, all right, and based on the problems that I just did here, try examples 6, 7, 8, 9, and 10. All right, try those examples. All right. So now going back, looking at example 6. So example 6, I see a negative underneath my radical symbol, and it's a negative number, and it's an odd index. The index is 3. So that means my final answer is going to be negative. So it's going to be negative whatever the cube root of 64 is. The cube root of 64 is 4. So the final answer is negative 4. Then I'm going to do the fourth root of 16. So when I go to my chart, I look for 16 in that x to the fourth column. The fourth root of 16 is 2. Because I have an even index and my radicand is negative, this answer is a non-real number. So in my math lab, you'll just click, non-real number. When it comes down to 15, the square root of 15, if you look in your square root column, the square root of 15, that's not a perfect number. So this answer is actually already simplified. And we'll actually look at some ways of simplifying numbers that are not perfect. But right now we're only talking about perfect numbers. All right. When it comes down to the cube root of 31, same thing. If I go to the cube root column, I don't see the number 31. So this is already simplified. You can't simplify it anymore. So that would just be the final answer. The square root of 15 would just be the square root of 15. The cube root of 31 would just be the cube root of 31. All right, so moving on. How do we deal with this variable stuff? All right, what about variables? So when it comes down to variables, first thing is this is a square root. All right, so x squared is the same thing as x times x. So I'm kind of going to do it the long way first, but it's just x times x. And so you're trying to find the square root. So what you do is you circle your variables in pairs. You circle them in groups of 2. So if you notice, I only have one circle there, one circle. So that means that my final answer is x, and the 1 represents the one circle. So one circle. What about x to the 10th? The square root of x to the 10th. There's an imaginary 2. We don't normally write the 2 for square root, but it's going to be helpful to write that, especially when we start getting the cube and fourth roots. If I had to do x to the 10th power, then I'm going to write x out 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you're going to group them together in pairs of 2. So I have 1, 2, 3, 4, 5 circles. And what's inside those circles? X is inside that circle, those circles. So I'm going to put X and 5 for 5 circles. Now, of course, you don't want to have to do that every single time. So what I'm doing is I'm dividing my exponents by 2. Now there's one extra step you have to do. All right. So you're talking about square roots, and this is only for the ones that have like an even index. So there's one extra step. Whenever you're taking the square root, you look at your final answer. Remember, you can't take the square root of a negative number. So if x was a negative number, all right, this wouldn't work. So your final answer actually is anytime, let me just make a note. Anytime your final answer, so if my final exponent, I'll say, is odd, this is how it works. You must put absolute value around variable. So in that case, the final answer would be, instead of just x to the first power x, it's going to be the absolute value of x. That's because your final answer, so originally, the original problem is a square root problem. So automatically, if your final answer has an odd exponent, you have to put an absolute value symbol around it. That's how you protect it. That's how you protect and make sure that you're going to always have a positive number. All right, I know it's one extra step, but that's just what you have to do. So here, this ends up being the absolute value of x to the 5th power, because my final exponent is an odd exponent. All right. What about something like 13? All right, with 13, I have this square root of 16, and then I have this square root of x to the 6th power. Well, first of all, I can write this as the square root of 16 times the square root of x to the 6th. All right, you can write it separately. And we're going to be doing this a lot. The square root of 16, if you go to your chart, is just 4. And then the square root of x to the 6th is if you divide exponent by 2, that'll give you your final answer. So this is x to the 3rd power. Because my exponent for x is odd, I have to include an absolute value symbol. So it's 4 absolute value x to the 3rd. right, looking at example 14. All right, so for example 14, give me a moment, let me check and see. Okay. All right, for example 14, same thing. You're going to just divide your exponents by 2. So x to the 4th, the square root of x to the 4th is x squared. But since you have an even exponent, you don't need an absolute value symbol. Because if you put any number in for x and you square it, it's always going to be positive. So you don't need it. All right, here, when it comes down to cube root, you want to do the same thing. So for cube root, you're grouping them into groups of 3. So if I do x, 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 that's what x to the 3rd equals. I have one circle. So one circle. And what's inside that circle is an x. So this is x to the 1st power. Odd exponents, well, odd roots. So odd index, or what we call the root. Odd index, you don't need an absolute value symbol. All right, so no absolute value symbol. Needed, because remember, we can take the cube root of a negative number. So the only time you have to worry about absolute value is if you're taking even root, square roots, 4th roots, 6th roots. All those you need to watch out and make sure that your final answer doesn't have an odd exponent. If it does, you have to put absolute value symbol. All right, what about x to the 4th? Same thing. I'm going to write this x times x times x times x. So I have one group of 4. So that's one circle. So since I have one circle, this is x to the 1st power. So cube root and 4th roots works the same, just like square roots. You're just going to take your exponent and divide it by the index. So when I did the cube root, if I do 3 divided by 3, I get a 1. Same thing with 4th root. If I do 4 divided by 4, I get a 1. So that's how my final exponent looks. All right, looking at the 4th root. Oh, actually, pause the video. Try the next few examples. So try 17, 18, and 19. All right. 17, 18, and 19. All right. So now let's look at the 4th root of 81, x to the 8th. So this would be the 4th root of 81 times the 4th root of x to the 8th power. When it comes down to the 4th root of 81, I'm going to look at my chart and see if 81 is a perfect number underneath the 4th column. So here's my 81. The 4th root of 81, if I follow all the way over here, is 3. So the 4th root of 81 is 3. The 4th root of x to the 8, I take my 8 and divide by 4. So that's going to give me a 2. So this is x squared. Since my x is squared, I don't need an absolute value symbol. So my final answer is just 3x squared. All right, this is when you should get excited. If you see assume all variables represent non-negative values, that means that you don't have to worry about absolute value symbols because they're telling you to assume they're automatically going to be positive. Now, I do know like on the test, they like to put one where you have to put an absolute value symbol. So just watch out for that. But for the rest of this lesson, I won't be putting any absolute value symbols because you'll see this little statement here. Assume all variables represent non-negative values. So going through the square root of x to the 2nd, if you take that 2 divided by 1, you get x to the 1st power, which equals just x. When it comes down to the square root of 9x to the 6, this is the square root of 9 times the square root of x to the 6. The square root of 9 is 3, and the square root of x to the 6 is x to the 3rd. So this is 3x to the third. All right, I don't need an absolute value symbol because they have that statement listed. All right, so now let's look at some ones that have multiple variables. It's the same. So here I'm going to do the square root of 25 times the square root of x to the 6 times the square root of y squared. And I mean, you really don't have to write it separately like that, but I want you to see exactly what I'm doing. I'm taking each, the coefficients and both variables, and I'm separating. I have to take the square root of all three. The square root of 25 is 5. The square root of x to the 6 is x to the third, because 6 divided by 2 is 3. And then y squared divided by, y is squared. So when I take that 2 and divide it by 2, I get a 1. So my final answer is 5x to the third, y to the first power, or just y. All right, so I want you to pause the video and try the next examples here, 21, 22, 23, all the way to 24. All right. What I'm looking to see, because I don't see any ones that's not perfect. All right. All right, in the next lesson, we'll be looking at examples where you don't have any perfect roots, so you're going to have to do some more work. But here, remember what fractions you separate, you do the top and the bottom. So this is the square root of 4x squared over the square root of y to the fourth. The square root of 4x squared would be the square root of 4, which is 2. And then for my exponent for this 2, if I divide that by 2, I get a 1. When it comes down to the denominator, if I take this 4 and divide it by 2, I get a squared. So my answer is 2x over y squared. The cube root of 8x to the 6. This is the cube root of 8 times the cube root of x to the 6. The cube root of 8, if you go to your chart, is 2. The cube root of x to the 6, if I take 6 and divide it by 3. So divide by 3. 6 divided by 3 is 2, so this is x squared. So my final answer is 2x squared. Then when I get to this next part, the fourth root. So this is the fourth root of 625 times the fourth root of x to the 8th times the fourth root of y to the 12th power. All right, that's a 625. So I'm going to go up to my chart and see if 625 is a perfect number in the fourth root column. Here we go, 625. The fourth root of 625 is 5. So this is 5. The fourth root of x to the 8th, when I divide 8 by 4, I get 2. The fourth root of y to the 12th, 12 divided by 4 is 3. So your final answer is 5x squared y to the third. Same thing works for expression like this. You have x plus 1 and it's squared. So you just take your 2 and divide it by 2 because you're taking the square root. So your final answer would be that parentheses raised to the first power, all right, which is just x plus 1. All right. So now let's look at some rational exponents. All right, so rational exponents, you're going to see that rational stuff come up a lot. The word rational come up a lot. When you see rational, it's just a fancy word, a fancy way of saying fractions. So I always, when I see rational, I look at the word ratio. Well, how can you rewrite a ratio? You write it as a fraction. So rational means numbers that can be written as fractions. Right? So you'll see that a lot, but that's just what it means, fractions. So here, a radical, all right, the ones that we just dealt with, square roots, cube roots, and fourth roots, those can all be written with the rational exponent. So it says x to the 1 over n is just the nth root of x. So let me give you some examples. So if I have if we write the cube root of x, that's x to the 1/3 power. If I have the 4th root of x, that's x to the 1/4. Even above the square root of x, it's the same thing as x to the 1/2. So let's look at some problems dealing with the rational exponent. So I see 9 to the 1/2 power, where 9 to the 1/2 power is the same thing as the square root of 9. And what is the square root of 9? Well, the square root of 9 is just 3. And there's your answer. So you rewrite it. Whenever you see a 1/3, this is a cube root. So this is the cube root of 64. So then you will go to your chart, look in your cube root column, find a number 64, the cube root of 64. All right, so here, cube root, find your 64. The cube root of 64 we did earlier is 4. So that chart is helpful. So this is just 4. What about this negative 25 to the 1/2? Well, if I rewrite this, the negative is by itself. That negative is separate. The 25 is raised to the 1/2 power. So this 25 goes underneath a square root symbol. So the answer to this is -5. Now, this is different from, so 3 and 4 are different. If you notice, you see a parentheses now around a -25. So this becomes the square root of -25. And because I'm taking the square root, which is an even index, of a negative number underneath that radical symbol, this is a non-real answer. Right. So here, we're going to look at, still looking at rational exponents, but now they're throwing in a little bit with the, what properties of exponents. So this kind of continues our last lesson, properties of exponents. So here you have a power raised to another power. So you're going to multiply all your exponents by 1/2. So remember that 81 has an imaginary 1 as an exponent. So when I multiply that 1 by 1/2, I get 1/2. And then when I do half of 2, so 1/2 times 2 is half of 2, I get 1. And then to simplify this, 81 to the 1/2 is the same thing as the square root of 81. And the square root of 81 is 9. So this final answer is 9x. And I don't have to worry about any type of absolute value symbols because it says assume all variables represent positive values. All right, so try number 6, just rewriting number 6. Try number 6. 6 and 7 and 8. So try 6, 7, 8. Pause the video, try 6, 7, 8. All right. If you look at number 6, it says simplify. Well, there's really nothing you can do. The only thing that has a 1/2 is the x. So if I rewrite this, this is just 4 times the square root of x. So that's how you'll rewrite it. All right, the x goes underneath a square root. Same thing here. I'm going to distribute my 1/2 to everything in parentheses. So this is 4 to the 1/2, and this is x to the 1/2. Well, the square root of 4 is 2. X to the 1/2, I can just rewrite it as the square root of x, and that's your answer. Here, same thing. You want to multiply all your exponents by 1/2, top and bottom. So now you have 144 to the 1/2 power. Half of 8. So 1/2 times 8 is like taking half of 8, which is 4. 169 to the 1/2 power. And then this is y to the 3rd power. So half of 6 is 3. And then you simplify everything. Well, 144 to the 1/2 is the square root of 144. And then 169 to the 1/2 is the square root of 169. So when I simplify this, I get 12x to the 4th over 13y to the 3rd. All right. So now a second definition of rational exponents. All right. What if you have an exponent, like a number other than 1 as your numerator? So notice how you have x to the m over n. Well, this is the same thing as the nth root of x raised to the n power, or this can be the nth root of x to the n power. It just depends on what type of problem you're dealing with. So most of the time, if you're dealing with only numbers, you want to use this form. So when you're dealing with only numbers, so like the next examples, this is how you want to rewrite it. So I have an 81 to the 3 over 4 power. Well, that's the same thing as the 4th root of 81. And then I need to put the 3 on the outside. So the numerator goes on the outside. Well, what is the 4th root of 81? So if I go to my chart in the 4th root column, so 4th root way up here. 4th root column, I'm looking for 81. There's my 81. The 4th root of 81 is 3. All right, the 4th root of 81 is 3. So this is 3 in the inside, and you have a 3 as an exponent. So 3 to the 3rd power would be 3 times 3 times 3, which is 27. All right, so you try example 10. All right, last example, 64 to the 2/3 power would be the cube root of 64. And whatever you get, you want to square it. So the cube root of 64 is 4. And when you square 4, you get a 16. All right, that's it, guys.